back to the channel, guys. Today we're going to be talking about confidence intervals. So they're part of probability and statistics. So we'll start with simple confidence intervals, right? And then we'll move on to a more complicated problem that you might need extra steps. So a simple problem would be something like this. The mean height of plants at a farm is 4.6 meters. The standard deviation is 0.25 meters. Construct a 68% confidence interval, right? So this is a simple problem in terms of they're bluntly giving you the mean, the standard deviation, and they're asking for a common confidence interval. Right, so there are three common confidence intervals. So 68%, it is accepted that the formula is mean value plus or minus one standard deviation. So you have the mean value 4.6 plus or minus one standard deviation, in this case 0.25. And then the formula for 95% confidence interval, another common, probably the most common confidence interval that they could ask, 95%, it's mean value plus or minus 2 standard deviations in this case. And then the third common one is 99.7% confidence interval. The formula is clear, it's just simply mean value plus or minus 3 standard deviations. So these are the three numbers you have to memorize: 68, 95, and 99.7. It's mean plus or minus 1, 2, and 3 standard deviations respectively, right? So that's why I'm calling this a simple problem. So to do it, you just use the top formula because they want 68% confidence interval. They gave you the mean, they gave you the standard deviation. Just fill in the formula, you have the answer, right? But the thing in red there, it's saying that you need to use the Z tables for any uncommon values of confidence intervals. So if the question was 99% confidence interval, it's a bit more complicated in terms of the numbers are not common that you have memorized, like 1, 2, 3 standard deviations. You actually have to go to the Z tables to find the number you have to put in for the number of standard deviations, right? The mean is still there, but plus or minus, it could be 1.2, 1.5, 1.96, 1. Whatever standard deviations that you need to put in depending on the value you get in the Z table. So if the confidence level or confidence interval is not one of those three, then you cannot use these formulas. You have to find the value to put in the number of standard deviations, right? So in this case, a simple example, 68%, we just use the top formula, the first one. So it's the mean, 4.6, plus or minus 1 standard deviation, which is 1 times 0.25. And then when you do that, you get, for the lower range, or the lower limit, which is 4.6 minus 1 standard deviation, it'll be 4.35. You put the mean in the middle, and then you're going to have 4.6 plus, this time, 1 standard deviation. And then you get 4.85. So that's a simple example, and then that'll be the answer there. That's the confidence interval. The mean is between 4.35 and 4.85 at 68% confidence interval, right? So let's look at a more complicated problem, right? So here you have, in a random sample of 350 food outlets in 2016, 56 of those had kittens that were deemed unhygienic by the Irish Food Authority. Construct a 99% confidence interval for the percentage of all food outlets with unhygienic kittens in 2016. Right, so why am I saying this is a more complicated problem than the other one? Well, there are three main issues here, right, that you can see. The first thing is the confidence interval is not a common one. It's not 68, it's not 95, not 99.7, it's 99. So you have to seek that, you have to find that in the tables. It's not a simple thing where I just say it's 2 or 1 or 3 standard deviations. It's some other value, right, probably with a decimal point, that I will have to find in the tables. That's one issue. Number two, we don't know the mean. They didn't tell us any mean or the standard deviation as well. So that's the third problem. The other problem, as you noticed, it clearly or bluntly gives you the mean, they gave you the standard deviation. It's just popping in those formulas and it's done. But this one, there's no word mean in there. There's no word standard deviation in there. So, okay, it's a different one. So those are the three issues you have to tackle. So if you tackle each one of those, then effectively you just answer the question. Okay, so this is what the distribution or the bell curve looks like in our question, right? So it's a 99% confidence interval. You have 99% in the middle there. So you want your data, 99% of the stuff to be from the mean on either side. You want all that overall stuff to be 99%, right? So you put 99% in the middle of your bell right, of a bell curve. So that bell curve is representing 100% of the data, and you want 99%. So the mean is right there in the middle. You want 99% to be in the middle of that, and then to the either side of the mean, right? So what does that mean? That means that if you have 100%, right, of the data, 99% is in the middle. So that means there's that 1% left, and it's either on either side of that data in the middle that you want, right? So it's important just when you're doing this to just visualize what it looks like, right? So you put 99% or whatever it is, 80% confidence interval, whatever, you put that in the middle of the data, right, in the middle of the bell curve, and then you find the remainder. So in this case, the remainder is 1%. So because you have these two tails that are symmetrical, that are equal, because the remainder is 1%, it's 0.5% on the left, 0.5% on the right. This is what it looks like, right? And the interval is the thing in the middle, right? So these are the Z tables, right? So in the Z tables, you can find the Z value or the number of standard deviations that you need. So if your Z value is 2, that means you need 2 standard deviations, which is 95%, right? If your Z value is 3, that's the 99%, and so on. And there's other Z values in the middle, right, that are not like that are not whole numbers, like 2.5, whatever. So these are the uncommon ones, like the 99%, right? So you don't go off in the tables to look for 99%. That's the point of drawing the bell curve. You go in looking for 99.5%, because the Z tables, what it does is it gives you the mapping from 0, from all the way to the edge here, from 0 to the value, the maximum you want. But then the thing is, because our data is actually in the middle of that, we put the 99%, but we have to take into account that the Z tables gives us from 0 to the value that we want. So it's going to be 99% and then plus this 0.5%. So it's going to be 99.5%. That's the Z value we actually want, right? That will represent our data, because our data is kind of, you can imagine as if our data is shifted by 0.5% so that it's right there in the middle, right? So it's shifted by that. So to actually find the value where it will be, the maximum value, we have to account for the fact that it's shifted by that 0.5%. So that will be 99.5. So that's the value we'll be looking at. Again, to remind you, why are we doing this? We have three common values, 68, 95, 99.7, which will be just straightforward, 1 plus or minus 1, plus or minus 2, plus or minus 3 standard deviations. In this case, we have 99%, so we have to actually find the Z value or the number of standard deviations we need, right? So we go on, and yeah, just to note, this is 0.5%. We're going to add the 99% in the middle, the red part, and then we get 99.5. So the value we're actually looking for is not 99, it's 99.5. In the Z tables, it gives you in decimals, right? It doesn't give you as a percentage. So 99.5% in the Z table is 0.995. So we had that value, right? So the value in the, all those values in the middle, the numbers that are not bold or dark, those are the percentages, right? So we just look for it, and then this is 99% or 0.995, right? So that's the closest value. 0.9949, the one to the left. This one here also works, like, because they're the same. They're both close to 99.5, right? Either one of them work. I just picked this one, and the 0.9951. So you have to pick the closest value, right? Usually there's just one closest value. Okay, so you pick the closest value, and then you find the corresponding Z value. So that's the amount you want, and then you find what Z value does that represent. So how many standard deviations does that represent, right? So we go and we find the row is in 2.5, the column is 0.085. So your answer starts with the 2.5, and then the last number that comes out of the 5 is the 8. So the Z value is 2.58. So the number of standard deviations that we will have if we had the mean, so to be mean plus or minus 2.58 standard deviations for 99%, right? So that's the value we'll be using. So again, this is our problem, and we already said that we have 3 issues. We have kind of corrected one of the issues. That's why I'm putting it in green there. So one of the issues was the uncommon confidence interval. So 99%, we don't know how many standard deviations to put in. So we went in the tables, we found that the value was 2.58. Now the other problem is they didn't give us the mean, and of course they didn't give us the actual standard deviation, the values for those, like the problem in question 1. So if we knew that, if we knew the mean, then the problem will be finished. Then we would just use the Z value that we found um, um, as the number of standard deviations. So it would be the mean. If they give us the mean, it would be the mean plus or minus 2.58 standard deviations, right? So that's what we'll be using. But then the thing is, we don't know that mean, so we can't go there. And we don't know that the standard deviation that we'll be multiplying the 2.58 with. So we still have those two problems. So we actually have to use a different formula, which is another common formula. Not as common as the other ones, but it's a common formula where you have like a samples. So this is talking about standard error instead of standard deviation, right? So when you have like a sample, so when the question is samples and stuff, we don't know the standard deviation of that sample, right? And we don't know the mean of the population. So it's a sample set of the population. So here you have to use something called standard error. The formula looks the same. So the p hat, it's equivalent to the mean, right? So that's equivalent to the mean in the other formula. So the other formula is mean plus or minus z times the standard deviation. So instead of saying mean, we're using this p hat thing, which we'll talk about in a minute. Plus or minus z is still the same thing. It still means the z score. So we already found that, right? If it was 95%, our z would just be 2, right? If it was 99.7, we'll put 3 there or whatever. So that's the number of standard deviation. So we went on to hunt that down to find the z value because it was an uncommon value. We found it was 2.58, right? And then this thing there, that's kind of now replacing the standard deviation. That's how you calculate that value. So the formula still has the same structure. Some value plus or minus z times some value. Before it was mean plus or minus z times standard deviation, right? So in this case, it now looks like this. So what do those all symbol? What do these symbol mean, right? So the p, it's simply the sample of interest. So number of that divided by the overall population, right? In this case, our sample of interest is 56, right? That's the ones that were unhygienic. So that's our sample of interest, let's say. And then the overall population in this case is the total number of things in that population, in that random sample, right? So it will be 56 over 350. So that kind of gives us the percentage of those that were unhygienic, right? So 0.16. Okay, we get that's p hat. That's how you find it. Okay, and then the confidence interval then would be if you just sub in those values because n is just the number of samples you have, right? So in this case, the number of things you have in that sample. So in this case, you have 350 food outlets. So that's n. N is the total number in the population, the overall population, or the overall number of samples or subjects in that sample, right? So n is the big number, right? It's the 350. Okay, so you put in the formula because you know p hat now. P hat is 0.16. You know z is 2.58, and then n is just the total number of subjects in the thing, the ones that are good, the ones that are bad. So total, so the ones that were hygienic, the ones that are unhygienic, all of them. So the total is 350, and those were the things that were sampled in the data, right? So you just put in the formula, confidence interval equals 0.16, which is the p hat, plus or minus z is 2.58, times the square root of this thing. So you just put that in the calculator, p hat, and then you create the confidence interval. So for minus, you put 0.16 minus 2.58 times this, and then you get 0.11. You put the mean in the middle, and then you do again 0.16 plus this time 2.58 times the square root of p hat plus p hat times 1 minus p hat over n, which is 350. You put that in the calculator, you get 0.21. So that's that question there. And then again, you can have another problem here where you have in a random sample of 250 farms with a good level of cleanliness in their milking facility, 19 were found to have high bacteria count in their milk, right? And then in another random sample, again 250 farms with a bad level of cleanliness this time. So the other one's a good level of cleanliness. This one's a bad level of cleanliness in their milking facility. 64 of them were found to have high bacteria count in their milk, right? Construct a 95% confidence interval for the difference in the percentage of farms with high bacteria count in their milk between the two levels of farm cleanliness, right? So this is a more complicated problem in terms of you have two samples or you have two groups, right? So both groups have 250 farms. One group have 250 farms. They had good level of cleanliness, all of them. But in those 250 that had good cleanliness, 19 were found to have bacteria, right? You have another group, 250 farms again. All of those 250 have bad level of cleanliness, and 64 of those were found to have high level of bacteria in their milk, right? So you have two samples, and you have to find a confidence interval of the difference in the percentages of those two samples or populations, right? So it's a more complicated problem in terms of you have two samples, right? Before the previous two examples, it was just one sample, right? So I put the Z score there, the Z tables there to just show you that the 95% is a common value, so you can just use plus or minus 2 standard deviations. Or some people, if they want to be really accurate, you can find it in the tables, it will be 1.96. But 2 standard deviations is acceptable. So you can find the value in the tables the same way we did in the previous example. So you hand down 95%. Remember, 95% will be in the middle. On either side, there will be 2.5%, right? So it will be 95 plus 2.5%. It will be 97.5%. So you'll be looking for 0.975 in the tables. And then you find it, you find the corresponding Z value. So this is just to demonstrate how to read the Z tables again. But you actually don't need this in this question. You can just use 2 because 95% is one of those common ones that is accepted to just use the number 2 standard deviations. 68%, 1 standard deviation. And then 99.7% is 3 standard deviations, right? So that's an acceptable concept, right? Those are the 3 common ones that are used like that. Right, but anyway, so in this question, we don't have a problem of going into Z tables, although I was just demonstrating how to read the tables again. You just know that it's plus or minus 2 standard deviations, right? So this is the formula when you have 2 populations, right? It's a common formula. You can find it in tables and so on. You don't need to memorize it. So this is the formula of confidence level when you have 2 samples and you try to find the confidence interval of the difference between those samples. So that's the formula there. You have P1 hat P2, so population 1, population 2. Z, it's still Z, it means still the Z score, that's 2 in our case. And then you have the square root of that. So when you're looking at a formula, sometimes formulas looks complicated or long. This one is kind of one of them, it looks long, but actually it's a simple one in terms of the symbols are just repeating. So really in that formula, there is P1, P2, Z, and N. 4 symbols, which you already know what they mean. P1 is just the fraction of the sample of interest over the population for 1, and then P2, it means the same for the population number 2. Z, it still means the same, either you get in the Z tables if it's an uncommon, or if it's a common value, just use the common value 1, 2, or 3. And then N is the total number of subjects in that population. So you have population 1, population 2, N1, N2. And then you just put the raw values in the calculator and then you get the answer. So you actually can boil down that formula to just 4 symbols. So it's actually not complicated. So P hat, like we did before, it's sample of interest. In this case, it's not those. So we are calling P1 is the population number 1, the one that they introduced first, the 250 farms that had good level of cleanliness. So of those, 19, that's the sample of interest, had bad level. It had a high bacteria count, sorry. So you have 19 over the total, so it was 250. So 19 over 250, you get 0.08, right? So that's P hat 1. That's done. We do P hat 2, which is the same. Sample of interest, in this case it was 64, high bacteria count over the total number of subjects in that population. You get 250. So 64 over 250, you get 0.26, right? So that's your P1, P2. The formula is half done. We still need the 2 more symbols, which is N1 and N2. These are just the total number of things, right, of subjects in each population. In population 1, we have 250 samples. In population 2, we also have 250. So they just happen to be the same. And then you just put those values in the calculator, and you just get the answer. And again, you just emphasize that 95%. You can either use the 1.96 or just the 2, because the 2 is accepted. It's a common value. They just round it up to 2, and 2 is used for 95% confidence. But again, If it was a different value, you go in the tables, hunt it down, and so on. So in this case, just to demonstrate using the Z tables, I'll just use the 1.96. But either one work. So 1.96, I already explained how to get that. It to be 95% plus the 2.5 on either side, 97.5%. Hunt that down, find the Z value, it will be 1.96, and then just put that then in the for Z. So put the values P1 0.08 minus P2 0.26 plus or minus 1.96 or 2. It's also fine because it's a common value. And then put the rest of the formula. Put a minus first, you get an answer. Put a plus first, you get an answer. So if you put that in, so if you put the 0.08 minus 2.6, you get minus 0.18, and then plus or minus. If you put the stuff after the plus or minus in the calculator, you get 0.06. And then putting it as a confidence interval, you just put the mean in the middle. You put that thing in your calculator, the whole equation with the minus first, you get this answer minus 0.24, and then you do it again with the plus this time, you get minus 0.12, and then that's your confidence interval, right? So thank you for listening, and see you next time.